I'll just introduce you briefly. So Chase Haddleton is an engineer at Chalk, where he works in the company's high-performance query engine. Before he joined Chalk, he was part of the equities data platform team at Citadel, building large-scale systems for market data. And he holds a computer science degree from the University of Waterloo, the much-renowned AI institute. Thanks, Chase. Over to you.
Thank you for the introduction. So my name is Chase Haddleton. I work at Chalk in engineering on our query and execution team. And so we're going to chat today about how we built a system to accelerate Python for real-time machine learning inference. Cool. And so I think a kind of good ground to lay first is what do we mean by real time. And so our kind of problem statement of sorts is that we're trying to get the right data to the right place at the right time. And this is, a very familiar topic, and many presentations today have kind of touched on this on real time. And I think we have a kind of unique perspective because we serve a kind of heterogeneous set of customers who all kind of have different workloads and have different requirements for different sets of data. And the big focus that we have here is actually doing computation at inference time for these online type workflows. And so that could be either you're computing, aggregation, materialized, or computed on the fly of event data, or even from a historical query to your database. Or it could be even the system gets raw inputs from you that need to be augmented, maybe by a system prompt and fed into an LLM, or embedding vectors that, we could compute similarity scores between and then feed that into some sort of LM. But the gist here is that, most of our workloads are these kind of you need an answer to a question that needs to know data that is up to right now. And so this is really important for a host of reasons. But basically, if you're in the fraud detection use case, right, you really kind of do end up in a scenario where you might care about what happened in the last second. And, this is the same for Rexus, where, being able to know more about what the users have been doing in the most recent time can actually be very impactful to the business at the end of the day. And so for freshness features, the latency there is super important. But the latency here also matters, right? So if you are, in a financial institution and you're doing portfolio risk computations, you might be blocking a trade from being submitted to a market exchange. And so being able to answer a question about kind of the state of your world that is up to date as of approximately now, but get that answer very fast can be very impactful to the business, because if you're out of date, you might reject something that you should otherwise have approved. And if you're slow, well, then the opportunity that was there might actually be missed. And so ultimately, a lot of bespoke custom solutions end up getting built to solve these problems. And so this is hard for a few different reasons. But the gist is kind of, there's a lot of moving parts here, right? We're talking about systems that, touch on machine learning expertise, low latency systems, scalar architecture. And all of these are kind of, generally different people at companies who kind of have these understandings. And so the platform teams kind of have to balance a pretty hard set of optimizations here to try to make a system that works. And then they're, implementing a platform that, works with a ton of different libraries, none of which were really kind of built to be plugged in together naturally. And so there's a lot of integration work required to, get your system to work end to end here. And we hear a lot of frustration from our customers when we talk to them about their, feature serving platforms and trying to get it to actually kind of fill all these gaps. And especially because, you're building it and you have these technical requirements, but you also have a ton of non-technical requirements for your users, where you're trying to build a system that can give them the developer experience that they want, right? Your MLEs will always want to test, iterate, deploy quickly, roll back quickly, and, integrate new data sources, new data types. And so this kind of just makes it a kind of constant toil on the platform teams to be, at the bleeding edge of building and getting new things to work. So I'm going to switch gears a tiny bit now that we're kind of on the same page here, and talk about an example query that we see in Chalk. And so this is a kind of a more smaller example here, where we're looking at this query, which is pulling some market review information And then it's doing some analysis. So it's feeding it into an LM. It's processing yet, but they're doing some aggregations. And then it's making some kind of final result that it then returns to the user. And this is kind of complex. Like there's a bunch of different systems at play here. Like it's talking to a bunch of databases and calling out to a bunch of APIs, and it's really like federating a lot of business logic around kind of a variety of different like data sources and things. And so keeping all of this aligned is quite difficult. And you could write one of these by hand. And in this like simple example, like, that could be reasonable. But as the complexity grows, keeping this stable is quite difficult, and making it performance is even more so. And so this is kind of where we have stepped in and designed a framework that kind of intermediates all of this. We kind of do all of the connecting to the data sources and determining how everything kind of connects, and then users can write simple queries where they just give some input and then ask for some output, and then the framework does the heavy lifting here to figure it out. And so to do this, we rely pretty heavily on a few kind of foundational definitions in our framework. And so features is the kind of like big first one to know about. And so this is what users kind of see. And in this scenario, it's just a Python class with some data types and a little annotation. And you can see that features are quite rich types. They can refer to each other. And on the right side, the user class here, for example, has a few features that are computed based off values using our expression syntax. And so the goal here really, though, is to like try to let users not think about kind of how what ultimately is a graph of feature definitions all tied together. And so we just kind of let them write Python that they're very familiar with. And then we kind of push all of the complex logic of solving their query planning to our dynamic query planner. And so there's kind of another major concept, which is called a resolver. And the resolvers there's kind of three main ways to define them. We saw the expression syntax, which we just talked about. But there's also just Python resolvers, which are just pure Python UDFs in the bottom left. And then we also have SQL resolvers, and those are often for like sourcing data from data sources, but users can just write SQL. And that's really popular for a lot of ML like data scientists, because SQL is like a very popular language there. So if we go back to that kind of small query that we were looking at, we can actually see that it's actually composed of over 24 resolvers internally, right? Because the user is really just giving us one input here. It's just some ID, and they're asking for some output here. And it's the dynamic query planner that actually goes and determines kind of the path through their data model that we have to follow to do all these computations. And so you can see that there's actually 9 SQL resolvers that read from Postgres here. There's like 4 Redis online store lookups for like pre-computed feature values. There's 5 Python resolvers here calling users code. And then there's 18 expression UDFs, which are those kind of underscore expressions that we saw before. And so this kind of leads into our main part of this talk, which is our symbolic Python interpreter, which is basically, if we look at that example Python resolver we saw here, we see that the logic here is actually fairly simple. And so our question was, well, if we want to give our users the best development experience, can we kind of build them a better world where they can write this code and then they can get something much faster? And we kind of started by looking at the resolvers that existed, and the Python resolvers our users wrote. And we found that most of them are actually fairly straightforward. Some if conditions, some simple arithmetic. Sometimes you have multiple return points. But in general, they're, fairly easy transformations on the data that needs to be done just to get it into like the next state for another resolver to do work on. And so we decided that, maybe we could actually write an interpreter that would process these functions and then transpile them into those underscore expressions that we saw before. And so the huge benefit here was that we could do this conversion once at query plan time, and then we could cache this result and then never have to touch Python in a query execution again, in the ideal case. And so what we see basically is Python resolvers in our framework are basically strict error schemas. They have some input schema, they have some output schema, and they're the same as expressions. And so that makes it quite easy for us to do these optimizations and chain them all together. And by removing Python, it's like a huge win on performance and removing guild contention. And so I'll go through a small, the same toy example, but, if we see the logic on the left, it gets converted to the expression on the right. And you might notice that there's a lot of expressions in here that are duplicated. So for example, you might see like the max column S minus column D and lit 0. That's in there twice. We heavily rely on our execution frameworks, common sub-expression elimination to optimize these. We could optimize them while actually doing like the transpilation, but it's not really necessary here for performance. And the way that this conversion actually works is we process the Python code in some context. And so, the inputs to that function, if we go back a few slides, there's these 4 inputs. And so you'll see that they turn into, the 4 inputs in the initial environment. And then as we process the Python code, we update the environment. And by update, we actually create new ones there because the environments are, they're immutable. And basically every value in the environment is an expression with a Python type. And yeah, they're just initially a column expression. They're basically just looking up a column in some sort of data frame or table. And there's some complexity here, especially when you get around to how you deal with branching and merging branches. But it's much simpler than I think many people would expect, where like you kind of just compute both branches and you compute the resulting environments, and then you just merge back up into the tree what the branch would look like using an if expression. And again, this kind of just goes on for eternity as you try to implement all of Python symbolically, where you find for loops kind of have like a similar experience where you process them and then merge back in. And this works for variable aliasing and early returns and everything else. And there's a lot of kind of cool areas you can look to optimize here. In the traditional interpreter or compilers class type exercise where, you can use shortcuts to make things faster. That's a bit beyond the scope of this presentation. So yeah, one thing we did note doing this was that, there was no way that we could implement all of Python symbolically. There's too much, our users can do in a UDF for us to actually support everything. And so we kind of have a few planned fallbacks here to make the kind of adoption and transition smooth. So we try to symbolically interpret all of the UDFs if it's enabled, and then you enable it using some of our annotations. And then if you do something that is not interpretable, for example, you import a random Python library that we don't have support for, or you add some checks that do explicit runtime validation checks, because again, we do this conversion once at plan time, and so there's a few things that we just know would be logically unsound for us to kind of compile away or compile out. And so these are kind of the fallback, so that no matter what a user actually writes, it will always still work in the framework. It just might not be accelerated. And then finally, there's kind of a big caveat, which is, as everyone here is, I'm sure, familiar with, the halting problem is unsolved. And so converting a Python resolver would be attuned to the halting problem. And so instead, we use gas limits to limit how much time we're willing to spend on conversion. And we'll bail out if we spend too much time trying to convert a function. And there's some complexity of tuning because, maybe you care less about query planning time, but there's still a cost at plan time. And so, you don't want to wait infinitely long. Yeah, so this basically is the kind of entire foundation for how we kind of use Python as a DSL for writing expressions. And this is kind of the basis for how we do accelerate Python at Chalk. And so, this has been a kind of amazing UX uplift, because we kind of took code that people already had running in our system and made it, an order of magnitude faster without them kind of having to do any work. And then, at the end of the day, this is really just Python that our users get to write, and they're very familiar with it. And so, it's kind of provides them with a really great experience where they don't have to learn necessarily a new framework if they want to onboard new users. And we also get some really cool benefits, avoiding the GIL and all of the Python heap allocation and function calling overhead. But also this lets us vectorize code that previously was row-wise, because the expressions are inherently vectorizable. So yeah, thank you very much.
Thanks, Chase. Great to see the evolution of the chalk engine over time. I mean, I have a question on that about from Python. So there was previously a Rust engine at chalk, and if we look at Tecton had this Rift engine, which they transpile their DSL into DuckDB, as far as I'm aware. So what do you see as the benefits of Velox? Is it just that you can keep pure Python and you're not restricted to, let's say, DuckDB style transformations, or what's your take on it?
Yeah, so we adopted Velox, which is an open source project from Meta, to do kind of the root of the compute for Chalk. We still heavily use Rust. We have a ton of Rust integrations into our Velox code, and we have like a fork of their library because we've done some tuning for real-time serving. We had a presentation at VeloxCon earlier this year if anyone's interested to see a little bit more about symbolic Python and also how we've changed Velox to make it work. But I think the pros of using Velox is you have this, fairly malleable framework, which was initially designed to replace their usage of Spark and Presto. And so it's just extremely powerful. And so we can customize it like so many different ways to work for both, low latency, 10 millisecond queries, but also the scale out workloads that people need for offline queries. And I think we'd have a lot more work on our hands if we were trying to adopt DuckDB for the same use case.
Yeah, I mean, they're slightly different use cases. And do you have any plans then related to scaling out these workloads across multi-host environments, or are you looking to leverage kind of data warehousing backends, or what's the plan there?
Yeah, I think for our online query use case, the service is essentially horizontally scalable on that front. I think for the offline use case, that's where it's a little bit more complex. But I think, the kind of popular avenue right now in these scale workloads is like, small sharded, like horizontally scaled. And then you use, cloud storage like S3 plus Iceberg or something to do the kind of underlying data layer there.
Yeah, great. And you guys raised a big round this year. Congrats on that. How do you get with all the money?
Hopefully, keep building, keep our heads down, and grow the team, and just keep going at it.
Right. So I have one more question. I'm going to ask about the big elephant in the room. So, transpiling, LLM assisted programming. Is Python the language of choice still? Is it going to be the language of feature definitions in the next couple of years? Because I think a lot of our community, including Hopsters, we're kind of heavily into the Python community, but I'm a little bit doubtful that's where we're going to be in the next year, 2 years. Will the level of abstraction be lifted up?
Yeah, that's a great question. I think you can look at the AI tools on like a few different fronts. But like one of the fronts that one of the camps I fall into right now is, there's so much Python in the world, and that means that the LMs have so much Python to use as a backing for all their training. And so I think that means that, as long as, humans like to write Python, they're going to ask LMs to write Python, and the LMs are really good at writing Python because they got a lot of it.
I think that's a really good insight there, because one thing I keep a close watch on is there's something called the Bird Brain benchmark for SQL. And the Bird Brain benchmark is basically all of the kind of the big data warehousing teams are contributing to it and trying to improve on it. It's going from text to SQL, so it's text to SQL. And you would think that LLMs are good, but they're scoring at about, I think, 76% when humans score at 91%. So we're so used to LLMs outperforming humans, but for some reason with SQL, maybe it's the declarative nature. I'm not sure, not enough annotated examples, but Python works really well. So, yeah, I think
you get a nice verification, like verifiable like system. If you as a human you write Python, you can ask the LLM to like help you write more Python. If it writes bad Python, Python, so you can correct it.
Exactly.
There's a nice.
Thanks, Chase. Is it okay to share the slides on Slack? And if there's more questions, we can jump in there. A question just appeared at the last second, but maybe we can take it offline. I think I actually asked a variant of that question already, but you can take it on Slack.